This is a lab exercise captured on video on the topic of crosstalk, taken from Lab 4 of the ME1400 EMI and EMC University courseware. Today we are going to share with you one of our lab exercises in the field of EMI and EMC, the crosstalk measurement and investigation in time domain. In the field of electronics, crosstalk refers to a phenomenon where an undesired signal, which is either voltage or current, from a transmitting source creates an undesired effect in another circuit. This is a term used to describe interference between conductors or circuits that are placed adjacent to each other. The objective of this lab exercise is to observe the crosstalk phenomenon, measure and investigate in time domain the factors affecting the crosstalk. To get the most out of it, you should view the video along with the lab sheet. Please download the lab sheet from the URL in which you can find from the descriptions. You may want to pause this video and read the lab sheet first before proceed with the video streaming. In this exercise, we are going to examine the effect of a high-speed pulse on a PCB trace to an adjacent trace. This lab setup makes up of an Adrian 7000 series oscilloscope and a Dreamcatcher ME1400 EMI and EMC training kit. This kit includes an EMI source module and a transmission line module. There are 3 high-speed pulses on this EMI source module. We are using the high-speed pulse for this setup. The high-speed pulse on the EMI source module is connected to the active trace of the coupled microstrip line. The microstrip lines have an edge-to-edge spacing of 0.56 mm and a couple length of 100 mm. Both ends of the induced lines are terminated with a 50 ohm SMA connector. Now let's measure the rise time of the high-speed pulse at the entry point of the microstrip line. We are using probe 1 to capture the signal, then press the stop button to freeze the signal for ease of analysis. With just one press of a quick measure button, we can get the rise time and peak-to-peak level of the pulse. The measured rise time is 1.4 nanoseconds and the peak-to-peak level is 3.34 volts. To view the crosstalk signal on the adjacent line at the near end, probe at this point. We are using 2 probes at the same time. Probe 1 to capture the high-speed pulse, which is the EMI signal, and probe 2 to capture the induced signals on the adjacent trace. Here you can see that the near-end crosstalk spike on the rising edge is a positive spike, whereas on the falling edge it is a negative spike. You can also see that the peak-to-peak level of the spike is 396 mV. Now give yourself some time to find out the near-end crosstalk characteristic. Next, we shall investigate the far-end crosstalk. Where's the location to probe? To view the crosstalk signal on the adjacent line at the far end, probe at this point. Now you can see that the far-end crosstalk spike on the rising edge is a negative spike, whereas on the falling edge it is a positive spike. The spike peak-to-peak level is 88 mV, which is much lower than near-end crosstalk. Why is this phenomenon observed? You can find the answer from the reference book recommended in our lab sheet or from our EMI and EMC teaching slide. Now we are changing to another coupled microstrip with bigger edge-to-edge spacing of 1.2 mm, about double the spacing of the earlier lines. And with the same high-speed pulse, we'll see how it changes the crosstalk level. To examine the near-end crosstalk of this wider spacing microstrip, I'm using probe 1 to probe the high-speed pulse at the entry point of the active trace and probe 2 at the near-end point of the coupled line. As you can see now, the polarity of the near crosstalk spot is the same as the previous narrow copper line, which was shown earlier in this video. However, the spot level is smaller now, which is 374 mV compared to 394 mV from previous narrow copper line. I'm probing the fine crosstalk to examine the crosstalk sign. As you can see, the fine crosstalk spots are in reverse polarity, which is the same phenomenon observed with the narrow copper line. However, the spot level is smaller, which is 76 mV compared to the previous 88 mV derived from a narrow copper line. This experiment concludes that the spacing between two adjacent lines does determine the magnitude of the crosstalk signal. Now we would like to examine how the length of a copper line affects the crosstalk level. This copper line has a 0.56 mm edge-to-edge spacing, which is the same as the first copper line, but with a shorter copper length of 50 mm, half of the length compared to the first setup. Use probe 1 to capture the high-speed pulse on the active trace and probe 2 on the induced near-end crosstalk point. As observed on the rising edge of the pulse, the induced signal is a positive spike, and on the falling edge, it is a negative spike. However, the signal is much smaller now. It is 157 mV compared to the previous 394 mV from the 100 mm copper line. Again, we are examining fine crosstalk on this 50 mm copper line for comparing with the 100 mm copper line. The same phenomenon is also observed on the fine crosstalk, which is a much smaller spot level compared to the longer 100 mm copper line. From these lab exercises, we can conclude that the spacing and the copper length of two adjacent lines can affect the crosstalk level significantly. So to avoid getting crosstalk interference from adjacent lines that carry high-speed pulses, you need to keep adjacent lines away from the high-speed lines at a sufficient distance. We have completed a crosstalk investigation on 3 copper microstrip lines. The microstrip line number 1 with copper length of 100 mm and edge-to-edge spacing of 0.56 mm induced the highest crosstalk level, be it at a near crosstalk or fine crosstalk, comparing to the microstrip line number 2 with the same copper length but double the spacing between traces, and the microstrip line number 3 with the same spacing between traces but half the copper length. You may be anxious to know what would be the impact on the crosstalk signal if a lower speed pulse is fed to the 3 microstrip lines. On an EMI source module, there are another 2 digital pulses with rise times of 3 nanoseconds and 6 nanoseconds for the next investigation. Feedback to us if you want to view this new exercise on video soon. This is one of the many complete resources for lecturers. Each of this university courseware comes with editable teaching slides that are good for 1 full semester lecture, training kit with editable lab sheets and solutions, and setup recommendation using instruments from Agile Technologies, a world-leading test and measurement company. To find out more on how you can benefit from this courseware, please visit dreamcatcher.asia/cw or agile.com/find/teaching solutions.